All right, welcome everyone to today's seminar, which is on the topic of valve leak tightness requirements. And all of this stems from the IEC 61511 standard. And specifically, what we're looking at is the Safety Requirements Specification section, where it requires you to document several attributes of all safety instrumented functions, and one of those is the output actions and performance requirements related to those output actions. So before I get started into the main topic of the seminar, I wanted to bring up that today's webinar is not something that completely stands alone, a topic that sits by itself. It's actually part of the Connexus core of training. And this is the Safety Requirements Specifications training course. It's one of the core courses in the Safety Instrumented System Design portion of our offering. And when I start getting into the lecture here, I am going to jump over to, I believe it is section 14. I'm sure I'll be able to find it shortly. There's section 8 on de-energized to trip and energized to trip. Section 11 on bypasses. And here we go with section 14, which is valve leakage rates. So now if you're interested in more of the Connexus training, I have also brought up the Connexus website, which is where our online training exists. And while we're more than happy to do all of our training live and in person, the most efficient way to do it is to just go into the Connexus Integrated Safety Suite, where everything resides, all the software tools and all the educational tools that you need to perform pretty much any technical safety task. So when I go to kiss.connexus.com is the integrated safety suite, and I sign in with our Connexus utilizes a single sign-in approach for security and easy administration of large enterprise accounts. You land as you normally do in the project manager section, where you have all of your facilities and all of your studies. But I'm going to go and I'm going to click along the top ribbon bar here. You'll see training, and Connexus Process Safety Training Center is our online learning management system, where not only can you upload whatever training you want and ensure that all of your employees are able to take it, but we offer a full suite of available courses. And that suite of available courses, it's not on a course by course basis. It's kind of, we kind of use the Netflix model. So for currently, I believe it is $995 per year. You have access to every training class that we have available. So right now I'm in the Safety Requirements Specifications training class. And so if you get a subscription, you can jump on into the class. And then if I go to resume course, I can find section 14, valve leakage rates, and you'll be able to see me do the official training. But I'm not going to do that today. I'm going to go ahead and give you a special presentation on the valve leakage rates. So let me shut down the online training that you can avail yourself of if you wish, and jump right into the material. So what we're going to talk about related to valve leakage rates, number one, is we're going to talk about the standards requirements. So what does the standard say with respect to how you determine, how you document the performance characteristics or the performance standards that you're going to want to hold the valves of your safety instrumented system to? Beyond the standards requirements, we're going to go into a discussion of the definition of leakage classes, because, well, tight shutoff doesn't mean the same thing to everyone. As a matter of fact, it's very hard to determine what exactly tight shutoff means. A lot of people use the term tight shutoff, and it's indeterminate what that actually means. Different standards use it, different people use it. There are different definitions of the same term. So if all you do is say, oh, well, for my SIS, I want all the valves to be tight shutoff, you're probably causing more problems than you're fixing simply by saying everything needs to be tight shut off, because you're lumping a difficult problem onto the people who are going to be implementing the safety instrumented system in terms of validation and testing. But you're not really clearly saying what you want either. So we'll go through all of the standards that talk about leakage classes, compare and contrast them, and give you a recommendation for what the most appropriate standard would be to use when you're determining those leakage requirements. The next thing we'll do is actually determine what leakage classes are appropriate. Once again, the easiest thing for an engineer to do, especially at an EPC company where you're just designing something for somebody else, handing them some paper, and then it's their problem, is to just say, well, everything needs to be tight shut off. Well, if you say that everything needs to be tight shut off, it actually needs to be tight shut offs. So you need to buy special equipment that is rated for tight shut offs. But even worse, you need to perform ongoing maintenance and testing to confirm that those valves stay tight shut off over their entire life cycle. Because as a lot of the salty dogs that have been in industry for a while know, that you can buy a leak tight valve, stroke it once, and it's no longer leak tight, because whatever process fluid you had in there just chewed up your seat, it chewed up your seals, it chewed up the ball or the plug or whatever type of valve you have, and now you're no longer meeting the as manufactured leakage requirements. And that could result in millions of dollars every year sending valves back to manufacturers to be relapped, to be rebuilt, and put back to that high tight shut off leakage state when it's actually not required to get the process to a safe state. So we'll talk about some approaches to set the leakage class. And where I'll kind of start out in my discussion is most of the time, you do not need tight shut off in order for the safety function to achieve its objective. It's exceedingly rare that you need tight shut off for a safety function to perform its safety objective. And if you do truly need a positive shutoff, using a single valve to achieve that shutoff is a wildly bad practice. So if you absolutely need isolation between one atmosphere and another, relying on a single valve to provide that for you is crazy. What you really want to do is you're going to want to put in a double block and bleed or a double block and pressure system that is going to give you a more positive isolation between those two environments. And that double block and bleed, double block and pressure assembly is going to be tolerant to a pretty significant amount of leakage, because all that leakage is going to a safe location instead of passing from one atmosphere to the other. So we'll start out by saying most of the time you're not going to need tight shut off, and we'll set you up with a methodology to determine the situations where you do, because in some cases some degree of tight shut off is going to be a necessity, but if you have it, you need to maintain it. And then finally we'll go over a valve's leakage specification workflow. where we explain when you're in that safety requirement specification phase of your project and you're developing your documentation, what activities do you need to undertake? And how do you document those requirements? And we'll give you a couple options for how you might want to document those requirements. Different organizations are going to have different needs. Sometimes broad general notes are okay. Other times, this is the type of thing that you're going to need to document valve by valve on its individual data sheet. So we'll come back to that, maybe even go into Vertigo a little bit to explain, to show you in an actual tool how to do this documentation. Okay, so in terms of standards requirements, it's the requirement is in clause 10.3. So 10.3 should set off a lot of alarm bells to you. This is that list. This is the clause in the standard that has that bullet point list of all of the things that are required for you to document for a safety instrumented system. Now, as I go into a lot of detail in the full SRS training class, most people, most competing software vendors do a horrible, horrible job of preparing safety requirement specifications, because a lot of them use what I will tell you is the worst method. The worst method is to go to clause 10.3, take that bullet point and turn it into a fill in the blank table on a safety function by safety function basis. That is an absolutely horrible way to prepare safety requirement specifications. We do not recommend it. We have a different approach I'll get to toward the end of the presentation when I get into workflow. But one of the things that you do need to document, one of the items on that bullet point list is that you need to specify a description of SIF process output actions and the criteria for successful operation, exempla gratia, leakage rate for valves. So the example would be leakage rate for valves, but another item that is actually documented elsewhere is that the valve closure time requirements is another one of those performance standards that you're going to want to specify for a valve. Now, let's talk about this a little bit more. So when you document that you need a certain leakage rate, and let's, go and be that lazy, engineer from the engineering company that, well, I've got a spot in this form I need to fill out for leakage requirements, and I'm just going to say tight shut off. Okay, well, what did you just buy? Well, when you specify something, we're going to get to the safety life cycle segment called validation. So validation is coming. And when we get to the validation phase, part of the validation process is going to every SIS instrument and ensuring that that instrument meets the requirements that were specified. So you put on your hard hat, you go out to the field, you find the valve, and you've got your data sheet, and you should use a data sheet for the valve. I'll explain later. And then you start checking off all the items, okay, make and model and direction and all those settings that, things that you can visually inspect to make sure that it's correct. But when it comes to leak tightness, you're going to need to actually perform a test. So for validation, if you say that the valve needs to achieve tight shutoff, you need to test it to make sure that it actually is tight shutoff. Now, you could do this in a number of different ways. You could take it, if you have isolation valves and upstream and downstream bleed valves, you could do a leak tightness test in situ with the valve where it is, but you might need to take it back to the shop to the maintenance shop to perform a bench test to make sure that the valve leakage requirements are achieved. And if it says TSO, how much is it allowed to leak? More on that coming up. The answer is, I don't know, not really defined anywhere, but I'll come back to that. Now, if a leakage rate or a valve leakage class has been defined in the SRS, not only do you need to check that during validation, you're going to need to check it every time you do a functional test of that safety instrumented function. Wow, that sounds like a lot of work. So let's say you have an annual test of the valve. It's not enough to just pump up the transmitter and watch the valve move to the closed position externally by looking at the valve stem. You need to do a leak test. So you're going to, once the valve is closed, you need to pressure up the upstream side and then basically measure how much is leaking through. And there are a variety of different ways to do that. Oftentimes, this requires you pulling the device out and taking it to the maintenance shop. Now, it gets even worse because if it leaks more than you specified, you've got to send it back to the manufacturer to get rebuilt, refurbished, relapped, new fittings, maybe seat replacements, depending on whether you have a soft seat or a hard seat. It's a very expensive proposition you just bought. So before we blithely go calling everything tight shut off and spending millions of dollars every year on testing and refurbishment, maybe we should look a little bit closer as to what we actually need. Okay, so again, TSO. What the heck does TSO mean? Is it defined anywhere? Well, we looked around and we found a couple of standards that are used to talk about valve leakage requirements. The kind of the two that go together, kind of the US and international version, if you will, would be ANSI FCI 70, and that is control valve seat leakage, and IEC 605344, industrial process control valve inspection and routine testing. Both of these are going to define the concept of leakage acceptance criteria or leakage classes. So more on that coming up. This is going to get the big star, the big check mark. This is the one that we're going to end up recommending that you use because it is extremely well defined and pretty ubiquitous. Now, searching for that infamous TSO, you can find TSO in several standards. You can find it in API 598, valve inspection and testing. It talks about TSO. I'm going to hold back on telling you whether or not it defines what TSO means. ISO 5208, metallic valves, contains the phrase tight shut off, and also API 60, specification for pipeline valves, also contains the phrase tight shut off. But to what degree they define tight shut off, describe tight shut off, and are those standards consistent with each other? Well, that leaves a lot to be desired. Okay, before we talk more about tight shut off, let's go about again, kind of the recommended practice from Conexus is to define what leakage class you need. Because when you define the leakage class, this ANSI standard and the IEC standard that talk about these leakage classes are going to give you a pretty airtight description of how the valves need to be built and what the maximum leakage criteria is for those valves in order to qualify for the leakage requirement. Now, the leakage classes in the standard range from class 1 is the worst. So class 1, we'll put our frowny face there. That's the lowest. And then class 6 is going to be the best, the tightest, the most leak proof. Now, in these classes, I'm going to draw kind of a distinction. It's not an arbitrary distinction between class 1 through 4 and class 5 and 6. And that distinction is going to be based on materials of construction. Classes 1 through 4 are going to allow you to do a metal to metal seat. Okay, so that means that in a ball valve, the ball is metal and the seat is metal. So you have metal touching metal performing your seats. It's hard to get a metal to metal seat to be extremely leak tight. You have to lap the surfaces to make sure that that they fit very tightly together. To get better leakage, better leak resilience, resistance against leakage, you're going to need to start moving the soft seats in class 5 and 6. And this is where the ball would be metal, but the seat would, for instance, be Teflon. And because you have an elastomer metal contact, you can push them together a lot harder and still allow the motion of the valve to happen. And that's ultimately what is going to provide that leak tightness, is a very tight interference fit between the moving surfaces. But if those surfaces are metal to metal, if that fit is extremely tight, well, then you suffer because the valve won't be able to move. Okay, so class 4 ends up being very common in process industries, especially in something like oil refining, because the chemicals in an oil refinery, specifically in a lot of petrochemical plants, are kind of dirty, kind of corrosive. They're a more severe service. So, for instance, if you have natural gas that you're purchasing from a utility, and you're putting that into a boiler, it's extremely clean. You could go ahead and put in that class 6 valve, no problem. But in a refinery, the fuel gas is usually a collection of junk collected from other process units that's going to contain a lot of salts, chlorides, fluorides, acids, ammonia, all kinds of particulates, coke. And when that gas goes through these valves and the valve moves, you start basically sanding the surfaces using those contaminants in the fuel. And the leak tightness you may have started off with in day 1 is going to quickly diminish to class 3, 2, or 1 after you stroke the valve a few times. So metal to metal is probably the best you're going to hope for in a lot of refinery services, a lot of big petrochemical services, where the materials that you're closing your valve against are severe. Whereas 5 and 6 are going to be reserved for really relatively clean services, relatively non-severe services. So through classes 1 through 5, I've already talked about I've already talked about the construction, and in the discussion of the classes, you see a little bit of just kind of how things are built. So, intended for double port, balanced port, single valves, piston ring seals, metal to metal seals. Is what you would use. So there's a discussion of the equipment that's used, or the materials of construction and the methods of construction. But, and there's a lot more on that in the standard that's not in this table. But now you're also going to start getting allowable leakage rates. And this is where things get interesting, because for class 1, there actually is no allowable leakage rate. So it can leak to whatever degree it leaks, as long as it was built using the methods and the materials of construction and techniques that were defined in the standard. But starting with class 2, we have an actual allowable leak rate. So for class 2, it is not allowed to leak more than 0.5% of the rated full open capacity. All right, now we actually have some criteria. So if you say that an SIS valve needs to be class 2, then when you perform your test, you need to measure how much leakage you're getting through that closed valve when you perform your function test and make sure that it's less than 0.5% of the rated capacity. Similarly, class 3 talks about 0.1% of rated valve capacity. Class 4 is 0.01%. So for class 4, dramatic difference there between class 3 and class 4, an order of magnitude less material that's being allowed to leak through. Now, when you get to class 5, instead of rated capacities, we start talking about actual amounts of material. So 5 times 10 to the 4th milliliters per minute per inch of orifice diameter for class 5, and 0.15 to 6.75 milliliters per minute for valve sizes 1 through 8. So this is our range of leakage classes, and basically the testing criteria that you need to confirm have been achieved when you're doing your periodic function tests. Now, so, okay, this is great. So what you're telling me, and I am telling you this, is that for a shutoff valve, you can specify its leakage class, and that's going to meet my SRS requirement. And it's also going to then carry over to writing my test plans, because if I have class 1, I don't need to check leakage, essentially, because class 1 has no allowable leakage criteria to it. So just visually, externally watching the valve stroke to make sure that you get a complete stroke is going to be sufficient for class 1. Everything else, you actually have to measure the leakage through, and that's going to be from 0.5% of rated capacity for class 2 all the way to 6.75 milliliters per minute for a class 6, depending on what you pick. Okay, so wow, this is good. I can pick these classes, I can write them down in my SRS, I can carry that information over to my test plans. But, well, how do I pick that? Well, we'll come to that in just a second. But before we do, I'm not going to leave, I'm a dog with a bone here. I'm not going to let go of that tight shutoff thing, because it's so many bad SRSs I've seen, and I have seen a lot of really bad SRSs. Having just kind of a TSO designation is something that you prefer not to see. What does TSO mean? Well, some people will say, oh, well, TSO, I actually mean that's going to be class 4 or IV, in accordance with the previous standards that we were talking about in the previous page. Okay, that's not written down anywhere. That would be just kind of some tribal knowledge. Some people might consider TSO to be class 6. But again, there's no definition of that. All right, so let's go look at the standards that actually talked about tight shutoff. So API 598 talks about the inspection and testing of typical valve types. It says that it is tight shutoff. Are you ready for this? For shell and backseat tests, if there is no visible leakage through the body liner, and joints, then that's a tight shutoff. No visible evidence of drops or wetting of the external surfaces. Wow, this doesn't even seem to actually apply to the process service. So I'm not gonna talk about that much anymore. Where else? We've got our ISO 52008 API 6D and RP 553. 528 just talks about valve design, if you will. 60 gives specifications for pipeline valves. And API 553 mentions that when you call something TSO, it should be class 5 or class 6, which that's a little bit concerning because it's a refinery standard, and 5 and 6 means we're talking about soft seats, which in a refinery is something, excuse me, that we would generally prefer to avoid. So yeah, all good stuff there, but after looking at this range of stuff, and then other standards beyond what is shown here might refer to tight shutoff. But I'll come back to this a little bit later on because a lot of people have got an interest in telling you how tight your valve shutoff needs to be. But what we're worried about right now is just compliance with the IEC 61511 standard. I'll come back to this when I get to the workflow. But based on all this discussion, based on all this research, this is why we came up with the recommendation that for leakage, allowable leakage through a valve, we're going to stick with the ANSI and IEC standards that define leakage classes, and that's what we're going to set. Now, great. You're telling me, I'm telling you, for every valve, you can say that there are no leakage requirements, or you can specify a leakage class 1 through 6. That's the best practice that I would give to you. Now, how do I determine what leakage class I need? There's the rub. Now I've got to go do some work, and the standard really only tells me that I need to do it. Doesn't tell me a whole lot about how to do it. What is the methodology? So I've listed off 4 methodologies from easiest to most difficult down at the bottom. Okay, the easiest way to pick leakage classes is just say everything needs to be tight shutoff, which is what a lot of engineers have been doing since the inception of the ISA 84 standard, which predates the IEC 61511 and 1508 standards, is, well, when in doubt, build it stout. I don't know. I'm just going to say we need tight shutoff. But that is easy for the designer. It is difficult for the person who has to pay for the valve. It is difficult for the person who needs to design the valve in terms of picking valve types and materials of construction. It's difficult for the person who has to test the valve and make sure all those leakage requirements have been achieved. And it's also expensive in terms of the ongoing maintenance for where you determine that because you stroke that valve once, it's no longer tight shutoff, so I need to send it back to the manufacturer and get it refurbished so that it is now once again tight shutoff. So I'm not a big fan of the most conservative approach because it's wildly expensive. Now, the second methodology is, I would say, probably the state of the art. It's not that good. But it's what most relatively good designs are based on, and that's just a qualitative assessment. So when you're in the SRS phase of the safety instrumented system design, you'll get a list of valves. So if you're using Vertigo, you can go into the final element list and one at a time, look through all the final elements. And for each one that is a valve, you will say to yourself, if this valve closes, so if I have a safety function, this valve closes and it leaks, is that okay? What is the consequence of the valve leaking through? So the team, through their gut feel, will say, a little bit of leakage is not going to prevent the safety function from achieving safe state, so I'm not going to put any tight shutoff requirements on it. And then the team might say, I don't know, if we close that valve but it leaks through, we're going to build up pressure, and that's going to allow the consequence that we're trying to prevent to occur anyway. It's just going to delay the consequence, for instance. So in that case, there will be a specification, and usually it will be the nebulous TSO. So again, what does that mean? Is that class 4? Is that 5? Is that 6? I don't know. All right. And so, yeah, that kind of nebulous stuff is pretty much kind of top quartile of what I've seen actually in industry. Now, the most difficult I'm not going to recommend either, and that's kind of the fully quantitative approach. So basically, what you'll determine is you'll calculate the leakage rate that's allowable by going in and doing a dynamic process simulation of the leaks to determine what the consequences of the leakage is. So you'll say, okay, well, if I have a class 4 valve, that is 0.01% of the rated flow, which translates into a flow rate of X over a period of time Y. And when that material is released, you can see what happens to the process as a result of that leakage. Fully quantitative, maybe over my 25 plus year career, I've seen done maybe a handful of times. It's exceedingly rare that you would do a dynamic simulation of leakage unless you have a very unique and a very dangerous situation where all that trouble is worth it. What we're going to recommend is this middle ground here. This is the Connexus best practice recommendation, is the semi-quantitative assessment workshop. So it's going to give you a little bit of the level of detail that you get by putting some numbers, but it's also going to use a workshop to make judgments instead of trying to calculate everything. So in the semi-quantitative assessment workshop, you're going to make a list of all your valves. For each of your valves, you're going to determine how much would leak for the various classes. 0.5% rated flow for class 2, 0.1 for class 3, 0.01 for class 4, and so on and so forth. Then you say, well, team, something similar to the HAZOP team. Okay, if this valve leaked this much, would the consequence that the LOPA scenario is trying to prevent still occur? If the answer is yes, then you need to go to the next highest rank. So it's a combination of a little bit of math, but it's still the ultimate judgment is going to be from a workshop. And basically, the leakage category you're going to pick is the lowest allowable leak rate, or the lowest category where the safety instrumented function is still going to be able to perform its action. So let's talk about this semi-quantitative workshop methodology in a little bit more detail. So workflow, what are we going to do? We're going to create a list of all the valves in our scope. Again, great purpose or great use of Vertigos, because Vertigo is going to give you this list. It's going to be the final element list in the SRS section. Next thing you're going to do is figure out what is the CV of all the valves in the study. This is going to come from the valve data sheets. Probably not something that you're going to document in your SRS. That's going to be your purchasing data sheet of the valve. Then we're going to calculate a leakage CV or a leakage rate. So what is going to be 1% or 0.5%? And this would be, again, that 0.5% is class 2. So we're going to calculate a leakage CV and then a leakage rate for every valve for every valve for at least the class 2. And then the other leakage classes you'll do on an as-needed basis. So we know a certain amount of material, a certain amount of gallons per minute or liters per minute is going to be leaking through this valve. Then we'll calculate a leakage volume. And what we're going to recommend is a 20-minute leak. This is 20 minutes is something that's kind of arbitrary. It's a common number that we'll use in risk analysis studies that basically says, I'm not going to allow a leak to continue forever. Eventually, someone is going to notice that there's a leak, something has gone awry, and we're going to manually close valves, or we're going to manually stop pumps, whatever it takes to stop that consequence from getting bigger. So whether you want to use 10 minutes or 60 minutes, there's no standard that defines this. 20 minutes is a very common number used in QRAs, but there's no standard or rules or regulations that are going to enforce this duration. Now, at this point in time, for every valve, you'll have a quantity. So 100 liters or 10 gallons leak through this closed valve. Then this is where we need to get our workshop team. So you say, okay, I've got shutoff valve UV 247, and it leaked 10 gallons of material through. You go back and you look at all of the scenarios that your SIL target is based on for the functions that are using that valve, and say, okay, if that occurred, what would the consequence be? Or more importantly, if I got that 10-gallon leakage, will that prevent the safety function from doing what it was designed to do? And that's how you make your determination. So if you run a calc on 1% or 0.5% of rated flow and say, well, that amount of material is acceptable to leak through, guess what? You've just determined that class 1 leakage is okay. And class 1 leakage means I don't really need to do a leakage test every time I do a turnaround, every time I do a functional test of the valve. Great. But if your team says, well, no, that 10 gallons that's represented by a 0.5% leak is going to prevent the safety function from doing its job, and we're going to have the consequence. You then step back one at a time. So, well, how about if it's only 0.1%? Well, how about if it's 0.01%? And you back up until you find the class that is going to make the situation tolerable. Now, of course, that might also be the trigger to say, forget about putting in a class 6 valve. Let's put in 2 class 4 valves with a vent and disposal line in between them, so that even if the upstream valve is leaking at 0.5 or 1%, it's getting vented off to the flare or a safe location. So because I have a double block and bleed, now I can go back to class 1 or 2 or 3 or 4 valves instead of trying to build and maintain a class 6 leakage system, which is exceedingly difficult to do. All right, so that's what a semi-quantitative workshop is. I highly recommend this approach. This is what we at Conexus recommend for those who want to go into detail and have a really good justification for what their leakage rates are. This is a darn sight more effective than just the purely qualitative workshop. So this is the methodology that we recommend. Now that we've given you the methodology, so we've explained what the leakage classes are, we've explained the workshop approach that we recommend to pick a leakage class. Now let's talk about requirements. And from here, I'm actually probably going to want to come back in and out of Vertigo a little bit as I do this. As a matter of fact, let me go ahead and minimize this and bring up Vertigo real quick. Go to Conexus KISS. I'm going to make it big so that human eyes can see it. Log in, and I'm going to go to my General Oil and Gas facility, which is our fictitious company that we use for software demonstrations and training classes and such. And I'm going to pull up, not that one, the SIS design basis. So now in the workflow, there are a couple of places where you can document the design requirements. So if you remember Vertigo, you kind of go, the workflow goes left to right. So we started out with kind of defining what the safety functions are, go into the SIL verification details, but now we're at the Safety Requirements Specification section. Now, the way that Conexus recommends writing specifications, the optimal approach, which is going to provide the highest value document with the least work, the most maintainable, and the most accurate over the life cycle of the facility, is our three-pronged approach, where we set general requirements, data sheets, and cause and effects. So that's our three-pronged approach, as opposed to the approach which is absolutely horrid, which is to treat the bullet list in clause 10.3 like a question and answer form. If you see software that treats clause 10.3 like a question and answer form, run the other direction. You're going to be documenting the same thing multiple times, so you're going to spend a lot more time, and it's going to be impossible to follow. You're asking for discrepancies in data because you're documenting the same thing in multiple locations. It's just a nightmare. So general requirements, sensor data sheets, which will be, there's data sheets for sensors, logic solver, final element, and IPF as a whole, and then the cause and effect. So now that we're here, you'll see that general requirements are things that we're going to write down once and have it apply across the entire safety instrumented system. So for instance, action on loss of power. So there's a general requirement for final control elements to move to their safe position by removing the power from the control element. De-energize the trip is the default configuration. So when I do this, what this allows me to do is write something down once and have it apply to everything, instead of having to document it separately for every safety function or document it separately for each individual component or piece of equipment. It's much more efficient. So now what you can do is you can set a general requirement for leak tightness. So let me back up to my my presentation slide. So a general requirement could be specified if that's a good thing to do. And it's generally not a good thing to do, but if you're with one of the people who's going to make every valve tight shut off, well, you don't need to write that for every safety function. You don't need to write that for every valve. You can write it one time. And, I don't know, everybody's plant, maybe it makes sense for your plant that everything is tight shut off. So if you're going to do that, you go back into general requirements, you add a new general requirement. So this would be in the Connexus documentation, that would be 5.07, I believe, and some number is how we would document the and it would be field devices, final control elements, and then I might define a subgroup like leak tightness. And then I would put in a requirement that basically says something to the effect of, and we always give ourselves a little wiggle room, unless otherwise specified, all valves used as SIS final control elements shall achieve a leak tightness of class 6. And then insert. So now, boom, one spec, everything, and find where I just dropped that, 507, there it is. Now I've just kind of dropped that in as a general requirement. It's going to apply to every valve in my plant. Okay, but I'm going to, as soon as I create that, I'm going to delete that because for most process facilities, that doesn't make sense. What makes sense for most facilities is to analyze each individual valve to determine what the consequence of leakage is. And then you're going to want to document that with the final element data sheet. So if I go back into Vertigo here and I go to my final elements, I can list off all of the valves. So let's say SDV101B is my high pressure separator inlet valve. I can click on this. Actually, before I do that, let me go here and let's view my list of final elements in a different location. And I know that SDV102B is only used in one location. It's only used in one safety function. And this is the safety function. So this is going to help you when you're making a determination, well, what safety functions is this valve used in? And then you could go to these safety functions and figure out what LOPA scenarios they are associated with. If you use a valve in more than one place, this assessment that you're doing needs to happen looking at every instance of its use. So this 101B valve here is actually used in 4 different safety instrumented functions. So I need to look at all 4 of those hazards when I'm determining what leak tightness requirement is going to be appropriate. Okay, let me go back to the SRS. I'm going to go to the final elements and I'm going to open 101B again. Now, this is the data sheet that I have customized. Those of you that use Vertigo know that we can customize this data sheet to add or remove different fields depending on what your needs and wants are as an operating company. This is kind of a typical layout that I would see that there's going to be a section here on a valve by valve basis that talks about tight shutoff. And what's interesting here is because of the kind of the relational database nature, I only need to fill this out once. So as we saw, this valve is used in 4 safety functions. So if you use that ungodly, horrible checklist approach to creating safety requirement specifications, you're going to need to recreate this documentation for 4 different safety functions because you use this valve in 4 different safety functions. Just run away from that garbage. This is the right way to do it. Okay, so for each one of the valves, we give you an option to say what is the target leakage class or what is the target leakage rate. I would recommend you just use target leakage class instead of leakage rate, but you know, to each his own. So what I'm going to do is I'm going to get rid of that target leakage rate by going into the study settings, SRS track field for final elements, tight shutoff. I don't want to see target leakage rate. Hit update, and now, boom, it's gone. This is our tight shutoff section. I don't need to see it anymore. Now, that doesn't mean it goes away. It just means you're not looking at it. Okay, so in this case, I determined that less than class 1 is okay. You might want to put in the tight shutoff notes field the documentation from the study that you did with the team. You could say that, you know, 0.5%, class 1 leakage of 0.15%, greater than 0.5% of rated flow is this. The team said that there is no consequence to that much leakage. Awesome. So that gives you the ability to not only document what the required leakage class is, but how you actually came to that decision. And then also, there's another flag here that says, is the target leakage required to achieve a safe state? Well, no, because it's less than class 1. But there's a more important reason why this field is here. Let's say that I have a double block and bleed arrangement on fuel gas going to a fired heater. I might say that the target leakage class is class 6. And then I'm just going to fill everything out. I'm going to leave this as no, and then I'm going to go to shut off notes. And then I can say something like, due to double block and bleed, leakage of less than class 1 will not result in a consequence upon activation of the SIF. SIF because leaked material would be vented to safe location, but NFPA 86 requires use of class 6 valve. Okay, so what did I do here and why is this important? I'm basically saying that the valve does need to be class 6, or actually I called it class 4. Let's do that again, class 6. But I'm saying that class 6 is not required for IEC 61511 compliance. There's another standard, and in this case, I'm just pulling a standard out of the air. I don't know all of the situations where NFPA 86 or any other NFPA standard would mandate leak tightness, but there are other standards out there that set what equipment you have to buy. But what we're saying here is, even though I'm buying the class 6 valve, I do not need to achieve class 6 to get to a safe state. And therefore, when I do my 1511 SIS validation, when I do my 1511 function testing, I'm not required to do a leak test to comply with 61511. Now, you still might need to do it to comply with NFPA 85 or NFPA 86, but we're making it clear that that leakage requirement is not part of 1511 compliance. It came from some other standard. So you've got that full set of documentation explaining where the requirements came from, where they apply, which is going to then define what you need to do when you're doing your ongoing testing and when you did your original validation. All right, I'm just going to cancel out of there, go back into the presentation slides. That was this last bullet point that says it allows you to document where other standards require some degree of leak tightness, but it's over and above what's required for 61511, and that might impact how often you do tests and the type of function test that you do, whether or not it includes a leak tightness step. All right, so with that, that is valve leakage rates. And again, this came right out of the Connexus Process Safety Training Center in our Safety Requirements Specification course. This is just one section out of 18 sections, so a lot of good material there. What did we talk about? We talked about standards requirements. What does 61511 say about leakage rates? Most of it came from clause 10.3 SRS. We talked about where in external standards from ANSI, from API, from IEC, that these leakage classes are defined, and we kind of made the recommendation to go with class 1 through class 6 as opposed to trying to use a term like TSO, which really has kind of loose and conflicting definitions in a lot of places. We talked about industry approaches to set leakage classes. At a minimum, you're going to want to do a fully qualitative workshop, but our best practice recommendation is to look at the leakage rates, look at the leakage quantities in a workshop format using that semi-quantitative approach to determine what leakage class is appropriate for your specific application. Once all that's done, you document it. And kind of making a very long story short, the best place to document this would be in a final element worksheet where you document the leakage class and a little bit of information to explain where that leakage class came from. But it's not out of the realm of possibility to just set a general requirement if every valve in the scope of your SRS is going to have the same leakage requirements, which is not out of the realm of possibility. And with that, that is valve leakage rates. I am Ed Marzell of Connexus. Feel free to contact me at any time if you have any questions, edward.marzell@connexus.com. You can find all my contact info on our website. Thanks for your attendance.